Root mean square value of alternating EMF. It is defined as that value of a steady voltage that produces the same amount of heat in a given resistance as is produced by the given alternating EMF when applied through the same resistance for the same time. It is also called virtual or effective value of alternating EMF. It is denoted by RMS or E effective or EV. Let us first understand what is the meaning of this definition. The definition can be a bit long and it can be a little bit tricky to understand. Okay, so the idea of all this lies in Joule's law of heating, which says that the amount of heat produced H is equal to I square RT. Yes or no? But then we know from Ohm's law that that I is V by R, right? So what we're going to do, instead of I square, we will write V square by R square RT. So we get a new expression, V square by R T. Okay, we're getting a new expression of the Joule's law of heating. So Joule's law of heating, it also depends on the amount of voltage that you apply to in the circuit. All right. So let us now use this. Okay. But in this case, instead of the voltage, we are going to write E for EMF. Okay. Right. So imagine we have a circuit just like before. We have a circuit and there is a resistance in the circuit. Then you have this AC. A key, this one. Okay, so this is the alternating EMF. So let's say this alternating EMF is applied for, again, let us take 10 minutes through this resistance of let's say 5 ohms. Okay, and the amount of heat it produces is 20 joule. Are you getting me? When this current, when this AC is passed through this resistance of 5 ohms for 10 minutes, it produces 20 joules of heat, right? So now the same circuit where we have the same resistance, now we are going to apply a direct voltage or a steady voltage. Okay, a steady voltage through the same resistance, which is 5 ohms. Got it? So how much will be the heat produced? If we first apply a small voltage, then in the same time 10 minutes, the heat produced will be small, let's say 5 joule. Understand? So we want the heat to be produced here to be the same as that produced by this alternating EMF. Okay, so what do? We increase this value of the steady voltage. On increasing, now the heat will be, let's say, 10 joule. Not sufficient. We increase it further. Now it will be 18 joule. We increase this voltage further. Now it will finally be 20 joule. How much is this? How much the value of this DCD, the value of this steady voltage that we are applying in this same circuit through the same resistance for the same time, that is producing the same amount of heat as that of the alternating EMF. This is called the RMS value of the alternating EMF. Are we understanding here? Just look at the definition once again. It is defined as that value of steady voltage. That means this one. How much steady voltage you apply that produces the same amount of heat in a given resistance as is produced by the given alternating EMF when applied through the same resistance for the same time. So how much steady voltage you are applying in the same circuit having the same resistance in the same time, so that the amount of heat produced by it will be the same as that produced by the alternating EMF when applied in the same circuit in the same time. So that value of steady current, steady voltage, is known as the root mean square value of the alternating EMF. Is that clear? So here also we will find the expression of the alternating. Let me rub this off first. Let the applied alternating EMF be E is equal to E naught sine omega t. This expression we already got in the first lecture of this chapter. Okay, so heat produced in a small time dt is dH, which is equal to E square by R dt. Yes. So which formula did we use? We used the Joule's law of heating. H is equal to V square by R T. Okay. Right. So what we are going to do, we are going to substitute this E with this expression. We will get E naught square by R sine square omega t dt. Let's call this sum equation 2. So what do we do now? Let us find the total heat produced in one cycle. One cycle means a time from 0 to capital T. Therefore, total heat produced in one cycle, that is time 0 to t, is how much? Is H. We are just going to integrate this expression, and again E naught square by R, that is a constant, we take it outside of the integration sign. So you have E naught square by R integrating of sine square omega t dt, and the time is from 0 to t. Got it? So here H is equal to E naught square by R. If you perform this integration, you will get t by 2. We are not interested in performing this integration. You can just remember it. Alright? Otherwise, we will be doing maths instead. Okay? You can just try this by yourself. Alright? Now, if suppose ERMS is the RMS value of alternating EMF, then it will produce the same amount of heat in the same time. And what time did we apply it? We applied for one full cycle. Okay, so therefore, which formula are we going to use? We will use this formula. Okay, but instead of V, we will write ERMS, and instead of small t, we will write one cycle, that is capital T. So therefore, we have H is equal to ERMS square by R capital T. Let's call this sum equation 2. Wait, I think equation 1 is already taken. Yeah, 1, 2 already taken. So now this will be 3 and this will be 4. Okay, so from 3 and 4. From 3 and 4 you have E RMS square by R T is equal to E naught square by R T by 2. So this T and this T will go, this R and this R will go. So you have E RMS is equal to E naught by root 2. A very similar expression. Here's another one that we get for IRMS. No? Or you have ERMS is equal to, again 1 by root 2 is 0.707 of E naught. Okay, or you can have ERMS is equal to 70.7% of E naught. Got it? So this is the final expression, the expression that gives the RMS value of the alternating voltage in terms of the peak value. A very small expression, but a very important expression. Thank you.